Let's take a quick look at surface area and how increasing the surface area affects the rate of a chemical reaction. Firstly, let's have a look at this mathematical concept of surface area. On the left, we have here a cube. Now the cube has a surface area of 6 centimeters squared, but just by getting our sword and chopping it in half and then in half again, we can actually get, instead of one cube, we get these 8 smaller cubes, but the surface area has gone up. So the size of each cube is smaller, but the total surface area is more. And then if we make the pieces even smaller, cut up each of these smaller cubes into even smaller ones, like this guy down here, well, we've got a lot more cubes. Sure, they're much smaller, but the total surface area has gone up yet again. Now, this is going to affect reaction rate because, as we know from the collision theory, reactant molecules have to collide. If there's more surface area, there is essentially more space for the reactants to collide. Like, let's say we put this solid into acid, right? Let's say we drop it into HCl, hydrochloric acid. Acid's always aqueous, cool. So this cube is completely surrounded by acid molecules, but remember, they can only actually hit on this surface, or this one, or this one, or the back one, the underneath one, or the other side one, right? We've got 6 square centimeters of surface available for the other reactant, in this case the acid particles, to actually hit. But in the middle example, yes, each cube is smaller, but when we add up all of the different faces of the cube, we have more area, which means more places for that HCl to come on down and react with. And in the last example, we've got twice as much surface area again. So really, we're just looking at the available space for the other reactant, in this case the HCl, to come and collide with. Okay, so we know we have to have a collision. We have to have a successful collision or an effective collision. But there has to actually be a collision. That's the thing. More surface area, more space for those collisions to occur equals more collisions. So let's have a quick look at a little prac here. What we're doing is weighing out some calcium carbonate, or one of my students is weighing out some calcium carbonate anyway. Now, calcium carbonate, here we go. Let's just look at the equation for that. And we are actually going to drop the stuff into HCl. I won't bother putting in the states, but HCl is always aqueous, all acids are. The calcium carbonate was a solid. Now, what we have is a metal carbonate, right? Calcium is a metal, and it's calcium carbonate, so we've got a metal carbonate. When you react a metal carbonate with an acid, you're going to get 3 things. Firstly, you're going to get a salt. In this case, the salt is calcium chloride. Balancing as we go, we need 2 chlorides. Okay, let's start with 2 of these HCl's. We're also going to get some water. And there's our 2 hydrogens from our 2 HCl's taken care of, great. And we're also going to get some CO2, and this is what we're going to use in this prac. Now, I'm not putting all the states in, but do realize that this is, of course, a gas. Okay, so we put a little G there. Sometimes people put an up arrow because it's a gas has evolved, so it bubbles up, but let's just stick with the usual convention is just to put the G for gas. Okay, so there's our equation, our reaction equation, and it's balanced because, of course, we can't create or destroy matter when we do chemistry. So let's weigh out some calcium chloride. What you'll notice here is that we have some calcium chloride chips, some chunks of it, right? We call these marble chips. Now over here, you can't really tell in the photo, but that's powder. It's the same stuff. Oop, there we go, calcium carbonate. It's the same stuff, but it's as a powder. One key thing here, 4 grams of the powder, 4 grams of the chips. Okay, so in both cases we had the same mass. All right, they were both 4 grams. Now that's a key thing to point out, because of course when you do a prac you only change one variable. We're looking at surface area, not how much stuff we used, right? So we had to use the same amount of calcium carbonate powder as we did of the chips. It really didn't matter that it was 4 grams, could have been 3, could have been 5.2, 4.8, whatever it was. The key thing was just to use the same mass of powder as we had of the chips. Now, this calcium carbonate got tipped into a balloon. So in this balloon over here, we have the powder version. This is the powdered calcium carbonate. This is the chips, calcium carbonate chips. And in the volumetric flasks, we have 50 mils of 2 molar, that's the concentration, and the acid we were using was HCl. So we've got 50 mils of 2 molar hydrochloric acid in this flask. We have 50 mils of 2 molar hydrochloric acid in this flask. Remember, we have to keep all other variables the same. We're looking at surface area. So we weighed out the same amount of powder and chips. We have the same amount of the same concentration of acid. Now, when we tip up the balloons and give them a bit of a shaky shake, the calcium carbonate falls down into the acid and reacts according to this equation that we've already looked at, and we're getting this CO2 gas formed. What's that going to do? It's going to go up. Where's it going to go? Into the balloons. So the balloons will inflate. So this is how we're going to measure the rate of reaction, by the rate at which the balloons inflate. Okay, so increased surface area, the reaction should go quicker. So the balloon with the powder should inflate pretty quickly, and the one with the chips, really not so much. Let's take a look. So here we have a couple of balloons, one with powder on the left in this example, the one with the chips, there they go falling in on the right, and you can see the one on the left, that balloon has inflated pretty quickly. Now the reaction's not quite finished, but it's just about done, and the balloon on the right is taking its sweet time to inflate. Okay, so we can see the flask on the right, we're still getting the gas evolved there, it was still going, and it will take quite a while for that balloon to inflate. Let's have a look at another example. Here we go. So the yellow balloon, what's that got? That seems to have the chips. The blue balloon in this case has the powder. Now when we're doing this prac, it takes a bit of a flick of the balloon or a bit of a shake to get all the calcium carbonate to fall down into the acid. But there we go, we can see some gas being evolved. That's of course the CO2. Now on the right, not so much because it's just about finished. Now this setup actually still had some calcium carbonate in the balloon, and there was some still up in the flask, but all said and done, it's pretty obvious that when the powder falls into the acid, the balloon inflates quickly. But when the chips go into the acid, it takes quite a bit of time. So here is the reaction proceeding. Now on the left we have powder, and how do we know that? Because the balloon is really big. And on the right we have the marble chips. How do we know that? Because the balloon's not as big. Okay, so maybe you can tell that there's still some reaction going on. It just looks sort of all cloudy. It's a bit hard to see in this photo, but you know, there was lots of gas bubbles coming up through the acid as the CO2 was evolved. Now the thing is, by increasing the surface area, we change the reaction rate. Okay, the one with the powder went faster. Yes, granted, but eventually this is what we get. The balloons will go to the same size. This is because we weighed out the same amount of reactant, the calcium carbonate, and we had the same amount of the other reactant, the hydrochloric acid. So given the same amount of the reactants, that will produce the same amount of product. So it makes sense that the balloons are actually the same size in the end. It's just that the one with the powder went to its size in about 13 or so seconds, and the one with the marble chips took about 12 minutes to get to that same size. So we had a much faster reaction with the powder. Here's another setup that some other students did. This is essentially the end product, not quite the end product. We can see here a little bit still going on, but essentially the balloons we can see have gone to the same size. Okay, so when we change reaction rate, we're not changing how much product we get, we're just changing how quickly the product is formed. All right, so there we go, increasing the surface area, more chances for collisions to happen, more space for those collisions to occur, and we know if we have the collisions, some of them will be successful. So if we've got more space, more collisions, more successful collisions, faster rate of reaction.
Don't forget to hit the like button. Yeah, and subscribe to It's Up Here. And here's another video.